Okay, I think we can start. So before we start, if you want to see your minor marks, you can come. I think many of you have already seen, some you have not. Yeah, I did not announce it, but they came for something else. I said, see your marks. So that's how it happened. Okay. So if you are interested in statistics, the highest is 20. Average I have not calculated, but I'm expecting, I mean, the sense is that it will be somewhere between 6 to 8, the average, and yeah. But I have to calculate the average. I have not calculated it. But greater than 10, I think 5 to 6 people are there, not more than that. Okay. Highest is 20. Okay. Anyway, so if you are interested in, you can come anytime in my office and check it out. Okay. Okay. With that, let us continue our discussion on Gaussian process, right? Or Gaussian process regression, to be more specific. So last lecture we started talking about Gaussian process, but we were doing two things parallelly: Gaussian process and then Bayesian statistics. So I was switching. Most of the thing on Bayesian statistics that are needed for Gaussian process have been covered. So we should be able to move at a faster speed today as compared to the last lecture. But let us start with what we have done in the last lecture. So remember that we are interested in using Gaussian process for solving regression problem, or we are interested in developing a surrogate model using Gaussian process. So that is the basic setup with which we are working, and in that basic setup we are working with the fact that what we are given is a data set that has xi and ti, and let's say I have n such data points. We are interested in solving a regression problem or a supervised learning problem. So t of x is equal to y of x plus epsilon, where epsilon is your model discrepancy, noise, and all those things, and epsilon is basically central limit theorem. 0 comma sigma y square is what I was writing. I mean, you can also write it as beta inverse, same thing, where beta inverse is equal to sigma y square. Sigma y is known as the standard deviation, sigma y square is the variance, 1 by variance is known as the precision in case of Gaussian distribution. It will not always be precision. In students T, precision has some other meaning, but in Gaussian distribution 1 by variance is known as the precision. So beta is your precision, which is nothing but sigma y square. I am introducing beta because, yeah, you should be aware of both of this, that both of these are equivalent. So I am bringing this into the picture. Okay. Now, and remember, Tx is a function, Yx is a function, and this is in a functional form. Now, the likelihood, we talked about what is the likelihood. We talked about the principle of maximum likelihood estimation and how it relates to how human make decisions or how human predicts. Many a time we talked about that. And the likelihood for this model is equal to, can you remind me what was the likelihood from last lecture? How do you define? It is d given theta is generally the generic sense. In our case, it is probability of t given x and all the parameters that are there that is unknown, right? So I'm not going to write those parameters, but I'm going to write it like this. Okay. Oh no, so y is also there in this case. So yeah, the y is also there in this case. So t, y, x, and there can be other parameters. I'm not writing those, right? So what was the likelihood in our case in this expression? We did it last time. What was this distribution equal to? What is the form of this distribution? Gaussian, multivariate Gaussian. What is the mean? Y. What is the covariance? Sigma square I or beta inverse I. The same thing we did last time, nothing new. So this basically is actually equal to Gaussian t y and then sigma y square I, or I can write beta inverse I n, right? So, and it is a Gaussian because I am only trying to I am constructing the likelihood, and likelihood is over the data. This is the data likelihood, and data I have is xi and ti. So in that sense, it's Gaussian. What is the dimension of t vector? N cross 1. Y vector is an unknown, but is a n cross 1, and in is a identity matrix of dimension n cross n, right? So this is our likelihood. Now in the maximum likelihood estimation, what is the principle of maximum likelihood estimation from last lecture? You maximize the likelihood to estimate the parameter. The parameter that maximizes the likelihood is your best or the most probable parameter. And we discussed that we cannot do it in this case, because in this case y bar is unknown, and I cannot treat y bar as a parameter, because then if I treat y or y bar as a parameter, I will only get y at those n discrete locations, which is not useful, because ultimately we will like to predict t for a new x. So we cannot do maximum likelihood estimation directly for this one. We cannot, and that follows from our last lecture directly, because y is discretized and we don't want to do that. So next comes the Bayesian philosophy. What is the Bayesian philosophy? Remind me the Bayesian philosophy from last time. What do we do in Bayesian? You should remember this. This is very basic. What is the Bayesian philosophy? Probability of whatever is unknown is to be considered random and modeled as a suitable probability distribution function. So the Bayesian philosophy is that whatever is unknown is uncertain, and stretching that, whatever is uncertain is random, and so it has to be modeled using some PDFs. Now in this case, what is unknown? In equation 1, y, and y is the equation 1 function. So we will assign a prior on the function y, right? We will assign a prior on the function y, right? What prior will we assign? Gaussian process. We will assume the prior of y to be a Gaussian process. And this is again something we did last time. This is where we ended last lecture actually, that prior we model probability of y as a Gaussian process 0 k x comma x dash semicolon theta k, right? Now, and now I will start going slowly, because until this point we had already covered. So now remind me, prior is supposed to represent your prior belief. So the distribution should be a function of your prior belief. But in Gaussian process regression, we assume the prior to be Gaussian process. So where is my prior belief here? Where is my prior belief here? Because I have assumed it to be Gaussian process. So I am forcing it to be Gaussian process. So if I have some prior knowledge, how will that be encoded into this prior? In the kernel, by the choice of the kernel. You remember we talked about that there are different types of kernel. So for example, if you are aware that your function is a periodic function, take a periodic kernel. If you are aware that your function is more or less smooth, maybe take a squared exponential kernel. If you are aware that your function is like a Brownian motion, then take a Laplace kernel, which is the exponential kernel, and so on and so forth. And some of this kernel we have already seen last to last lecture, that how the function changes, how the sample changes, right? So I will repeat. In Gaussian process, the prior is considered to be Gaussian process. However, your prior knowledge is encoded through the kernel. Okay, so it's a mix of convenience and belief. Belief, because your belief is getting reflected by the kernel, Convenience, because I am taking it to be Gaussian process, which will make my life simple. I will be able to do things analytically in most cases, and many things will be easy to follow. Otherwise, you will not be able to find out things analytically. You have to use sampling, things will be very slower or sometimes extremely slow, and so that does not help, right? So, in Gaussian process regression, the prior is modeled as a Gaussian process, and that's why we call it a Gaussian process regression. If it was modeled as some other process, I will call it that other process regression. As simple as that. However, your prior belief is reflected in your choice of the kernel. Is this clear? Is there any question on this part? This is fine? Now, if that is fine, in this prior, is everything known or is there something that is unknown? Theta k is unknown. What is theta k? The hyperparameters. Can you name them? Sigma, process variance, L, length scale parameter. These are the two right now. Sigma y is or beta is also sitting, but that is not yet here. So keep in mind that although I am assuming some prior, the hyperparameters of these priors are unknown, and that is to be learned, and that is to be learned from data. So keep in mind we need to find out this theta, because without knowing theta, I do not know prior, I do not know anything, I cannot make prediction. Keep that in mind. Okay. Why is theta called hyperparameter? Can you remind me? Because these are parameters these are variables that actually controls the parameters of Gaussian process. So these are parameters of parameter. What are the parameters of Gaussian process? Mean function and covariance kernel. Or if you write it in a Gaussian form, mean vector and covariance matrix, right? But this covariance kernel or covariance matrix is having a parameter or parameters. So these are like parameters of parameter. So that's why you call it hyperparameter, right? There are other hyper aspects like hyper prior. We will not go into that. But generally, when it's parameter of parameter, hyperparameter, prior of prior, you call it hyper prior, and that's the terminology we generally use. Okay, but we are not going to discuss that. Obviously, in a deep learning setup, hyperparameter has a different meaning. Those are parameters that you do not train but tune. But here the meaning is, here you train for hyperparameter. So do not confuse between, let's say, a deep learning and a Bayesian machine learning. Okay. In Bayesian machine learning, or specifically in Gaussian process, you train for your hyperparameter. At least in Gaussian process. In deep learning, learning rate, you don't train for it, you tune it. In deep learning, number of epochs, that's a hyperparameter, because you tune it, you don't train for it. Here hyperparameter means parameter of parameter. Clear? Any question? No. So now I have my prior, I have my likelihood, and we have already discussed that if there is something unknown, we can compute those unknowns by maximizing the likelihood. But we have also discussed that we cannot do that in case of the likelihood that is shown here on the slide, because y is sitting there, which is unknown, and we cannot work with that, right? So in Gaussian process, what we do is we do the following. We will be maximizing the likelihood, but we will not maximize the likelihood that was shown in the previous slide. We will maximize the marginal likelihood. In Gaussian process, the marginal likelihood is estimate. What is a marginal distribution? When some variables are integrated out. Probability of A comma B is a joint distribution. Probability of A, I will call it a marginal distribution, which from the sum law is equal to integration of probability A comma B dB. So that is the process. That process is known as the marginalization. So we will compute the marginal likelihood. Okay. So now, so in GP, the hyperparameters are obtained by maximizing the marginal likelihood, and this marginal is under quotation so that you can differentiate it from the usual likelihood. Okay. So what is my marginal likelihood? What was my likelihood? Probability of t given y. X was also there, but t given y, right? Marginal likelihood will be probability of t. Okay. Or if it was probability of t given y comma x, then marginal likelihood is probability of t given x. Obviously, comma theta will also come into picture, right? So probability of t given x comma theta. It is not theta k, it is theta. What is the relation between theta k and theta? Theta also includes sigma y square or beta. Theta k only includes the kernel parameters. The sigma y was sitting there, that was not included in theta k. So that is also included here. So theta is equal to this theta k plus this beta inverse. Okay. So if you take this plus this, you call it theta. I call it theta. Okay. So this is equal to, let's see if it makes sense to you or not. Probability of t bar given y bar comma x bar comma theta. Now all this theta might not be controlling this, but I am writing it, multiplied by probability of y bar given x, not bar, I mean it is at the below, y given x Do you agree with this expression I wrote? Right? So now, is there anyone who do not agree with this expression? It's basically the sum and product law. If you do a product of that, you will get t comma y given x comma theta, and then you integrate over y, so you get t given x comma theta, which is the left hand side. So inside the integral there is the product law, and then the integral is the sum law, and we have discussed product and sum law long back. So everyone follows this? If everyone follows this, you now tell me then, and you should be able to tell me, what is this distribution equal to? What is this? This is my likelihood. I was not writing the other terms, but this is actually my likelihood, t bar given y bar comma x, and theta is there. The theta will be only beta. The other theta is independent, so that does not matter. This is your likelihood. So what is the distribution? Gaussian of t bar given y bar comma theta will give me beta inverse IL. Right? Now let's see. What is this distribution equal to? The other one. Let's see if you can tell me. This, if you tell me, I will be very happy, because then I will know that you really understand. I will not say what. Let's see. What will be this distribution equal to? What is this term? Forget about the distribution. First, what is this term? This is the prior. Y given x is the prior, right? I mean, I did not write given x, but we know that kernel was x comma x prime, so it was actually y given x. So this is a prior, right? Now, can you tell me? I've given a very big clue. This is the prior. What will be this distribution? Gaussian process or distribution? Who thinks both process? And who thinks distribution? Let's go with process first. How many of you think process? You think process? Anyone thinks distribution? 2, 3, 4. Okay, 5. 4.5. Okay. So why do you think it is distribution? Theta parameters include sigma y. But that, how does it matter? That theta parameter also includes sigma y and L and sigma, the likelihood term. Does that count for anything? That don't count for anything. I mean, this theta is written for in a generic sense. Ultimately, some of this theta will be used, some of this theta will not be used. For example, this term will not use sigma y. You will not have a sigma y in this term. So now everyone agrees on that. What is the definition of Gaussian process? It's a collection, potentially infinite number of Gaussian random variable, right? And any finite number of that, when you collect, you get the consistent Gaussian distribution. So y given x is a Gaussian process. There is no doubt about that. But here it is not y given x, it's a y vector given x vector. So that means from that Gaussian process you have drawn y bar at the n locations. So from the definition of Gaussian process, that Gaussian process is now a Gaussian distribution. Right. So I am using the definition of Gaussian process here. And the definition of Gaussian process is telling me that when I only draw a limited sample at locations, I mean, that distribution will be a Gaussian distribution. So this is from the definition. A collection of potentially infinite number of random variables, any finite number of which follows a consistent Gaussian distribution. Right? So this will be a Gaussian distribution and it has to be of dimension, I mean, in this case, whatever the dimension of y bar is, which will be n by n. Right? So this is also a Gaussian of y bar. Tell me the mean. What is the mean? What is the mean? 0. So it was a 0 function. In that case, it will be a 0 vector of dimension same as the dimension of y bar, which is same as dimension of x bar. I mean x bar at the below, but anyways, which is basically n cross 1. So 0. And now the important part. What is the covariance? Kx comma x is a generic one. In this case, it is k xi comma xj, where I and j goes from 1 to n, because we have n data points. So this covariance will now be n cross n. So it is k of xi comma xj, where I and j both goes from 1 to n, 1, 2, 3, 4, n. Because x1 is, what will be then the first element? K of x1 comma x1. Second element k of x1 comma x2. Then k of xn minus 1 comma xn, k of xn comma xn. No, a training sample. There. Okay. I am not dividing component wise, but because that is not needed for explaining this. Why is?
Sigma y we are not considering here.
You can write. Who is stopping you? Where we are not considering? So what is the kernel here? So theta k will be there. Sigma y will not be there. Sigma y is there. Theta k includes sigma y. Theta k will be there. It will be function of theta k. I said sigma y will not be there. Sigma y is beta. Should beta be there? No, right? Okay. So this is basically kernel, and I'll write it as n. Okay, and it's a matrix. Okay. So, and this is from the GP definition. Where? So, Kn I comma j, let's say, is equal to the covariance kernel that you have selected, let's say exponential, let's say squared exponential, let's say periodic, and then you evaluate it at xi comma xj semicolon theta k. Why I am using that n in the subscript? Because I have n data points. That n in the subscript denotes that I have formulated this covariance kernel, or it's not no longer a kernel, it's a covariance matrix, by using n training data or nx. That's what this n denotes. Okay. So let me repeat once more because this is something new. The likelihood part is obvious. That the prior part, we assumed our prior to be a Gaussian process. But now when we want to compute the marginal likelihood, for computing the marginal likelihood, although my y is a Gaussian process, I have x at limited location or n location. So I formulate the prior for those n locations, which is like a finite collection of sample from a Gaussian process, which becomes a Gaussian distribution. Now the mean was 0, so it remains 0, but previously it was a 0 function, now it is a 0 vector. The covariance kernel becomes covariance matrix. Now the covariance matrix, the dimension will be n cross n because you have n points where you have measurements. And each element is what I have shown here. And remember, this covariance matrix is still not known because it's a function of theta k, and those theta k are unknown.
That 0 is the mean of
y bar. So the 0 is the mean of the distribution, right? The distribution is over what? Y bar. Okay.
will it be always possible that
It's a prior, right? It's you have assumed that I don't have any knowledge, let's assume it to be 0. When you make prediction, it will need not be 0 and it will not be 0, and you will see that. Okay. But let's take for the sake of discussion that you have some knowledge about the mean. You should not take it 0, put that in place of that 0. If you know that your prior mean is an exponential function, put it exponential of x. There is no problem with that. Yes. So let's say you want to model this 0 as a neural network. Take it as a neural network, the parameters will be unknown. So now theta k will also include those parameters. Now theta k will also involve the mean parameter. So all those flexibilities are possible. I am going with the 0, 1 because that's the most popular one. And in 99%, 97% cases, let's say, it works with 0 mean only. Okay. If you have adequate data. Okay. Is it okay? Why is it a Gaussian? It is Gaussian from the definition of the Gaussian process. The dimension is n because you have n observations, and it's only function of theta k because k is only function of theta k. That's all. Okay. So this is my marginal likelihood, but I need to evaluate this integral. Someone knows what will be this integral be? It's a convolution over Gaussian. Convolution of Gaussian is a Gaussian. Okay. I think that was the first question in the minor, in some other sense. But convolution of Gaussian is Gaussian. But can you tell me the parameters of this Gaussian? So let us see. I'm going to box it. So now this is equal to a Gaussian. Okay, first thing first, the Gaussian is over what? Which variable distribution are we talking about? Look at the left hand side. T bar, I mean T vector. But now you have to give me the mean. What is the mean? What is the mean? Let me first, y bar could not be there. You have integrated y bar. So y will not be there. Let me give you the answer and then I'll tell you how it is coming. It's very simple. The mean is 0. Okay. And the covariance matrix will be Kn plus beta inverse In. And this we will call as Cn. We will now discuss how this is coming. Okay. Okay. And you know this. You will realize that you know this. Okay. So let us see. This is fine. So now let us see. Let's take y is equal to ax plus b. Okay. And let us also take x is a Gaussian with mean mu comma lambda. So this is the precision matrix. Okay. I can write sigma also, does not matter. Okay. Does not matter. So now tell me what is the expectation of y from the above expression. Expectation of y is equal to a expectation of x, which is mu, plus b. Okay. What is variance of y or covariance of y, whatever you want to write? A, not a square. A is a vector or matrix, I had not said, right? So a, I mean, I can write it covariance and that is better, but a covariance of x, A transpose plus in this case 0. In this case it is 0. Yes, assuming that B is constant, right? This same thing I have used previously. Okay, so now let me also add a covariance here. Let's call it, this was lambda, right? So let's call it L. Okay, plus L, so let's say, okay, wait, let me make it easier, plus epsilon, where epsilon is from a Gaussian with 0 comma L. So now what will be the covariance? It will be covariance of Ax, which will give you a covariance of X A transpose, plus covariance of B, which will give you 0, plus covariance of epsilon. Obviously, I am assuming X and epsilon to be independent. Covariance of epsilon, which will give you L inverse. Everyone follows this or not? So what is covariance of this? Mean of this, let's say. So here also plus 0 should come. I have not written that. Now you will say expectation of y is equal to A expectation of x plus expectation of b plus expectation of epsilon. Agreed? A expectation of x is A mu, expectation of b is b plus expectation of epsilon is 0. So A mu plus b plus 0. Agreed? Let's go ahead. Covariance or variance, whatever you want to call it, let's say covariance of y, okay, is equal to covariance of Ax plus covariance of b plus covariance of epsilon, assuming these three are independent, which it is. Now covariance of Ax is equal to A covariance of x A transpose. Covariance of b is equal to 0. Covariance of epsilon is equal to L inverse. So you end up with this expression, which is equal to A Okay, this is fine. Now what is probability of y given x from this? From this, tell me what is probability of y given x. What is the distribution? Given that epsilon is Gaussian. What is the distribution? Forget about parameter for now. What will be the distribution? Gaussian, because x is conditional, so x is like a constant. So it's a Gaussian distribution. It's a Gaussian over y given, what is the mean? Ax plus b. What is the variance? Covariance? L inverse. See, this expression and this expression are equivalent actually. These two expressions are equivalent. Okay, I have not even integrated anything. They are just exactly the same. You can write it in form of a linear equation also, because Gaussian, you know, linear combination becomes Gaussian. So it's exactly the same. There is nothing else here. And this follows directly from this expression, t plus epsilon, t equal to y plus epsilon. The probability of t given y was Gaussian. There is no reason that this will not be Gaussian. Right? And what is probability of x? This too I have already written. So x given mu comma lambda inverse. What is probability of y? Integration. This is the actual convolution, the generalized convolution of Gaussian. This is Gaussian over y given, what is the mean? Written at the top, a mu plus b. There cannot be any x. I have already derived that. A mu plus b. And what is the covariance? A so just to repeat whatever we did. So it's very simple. When you have this kind of thing, all you need to do, when you have to find out, let's say, the parameters of y. In the conditional, it's already always in terms of x. But when you are integrating on x, you have to find out or substitute the mean and covariance of x there. That's what has been done if you look into it carefully. The y, expectation of y, when I'm calculating, I'm integrating out x, and so mu and lambda is now appearing. Okay. So now go back and substitute. What is our a in our case? In our case, what is a? A is 0, I think. What? A is of the likelihood. Look carefully. A is in the probability of y given x term. Where is a sitting? Y given x is having a. The conditional distribution has a. This distribution has a. This distribution does not have a. So this is what distribution? This one. Right? And where is it? This is which distribution? This one. Okay, so you are right, I think. So a is 1. Right? And expectation of y bar is equal to 0. So that is why the mean comes out to be 0. Correct? What is b? B is 0 actually in our case. And then what is mu? What is mu? 0 from here. What is lambda inverse? Kn, again at the top. So what is A, which is 1, lambda inverse A transpose, so 1, lambda inverse 1, so lambda inverse. What is lambda? Lambda inverse is Kn, so that will be Kn. So that Kn is sitting here, plus L inverse. L inverse is beta inverse I. So you end up with this expression. I'll repeat. Okay. We started with T is equal to Y plus epsilon. Okay. And I have n data points based on which I want to train. So the likelihood probability of T given Y is a Gaussian with mean Y bar or Y vector and covariance K, not K, sigma square I or beta inverse I, right? But we cannot maximize this likelihood because the Y bar is unknown or Y is unknown, right? And there is no point in finding out Y bar, that does not help in making prediction, and Y is unknown. So then we assign a prior, because the Bayesian philosophy is whatever is unknown you assign a prior. What prior we assign? Gaussian process. What covariance kernel we select? Based on the problem at hand, right? Based on the problem at hand. So that gives me this one. So now this covariance kernel has theta k sitting there, which is unknown. The likelihood has beta inverse or beta sitting there, which is unknown. We need to find those. How do we find that? We find that by maximizing the marginal likelihood. That is the maximum likelihood estimation only, but instead of likelihood we are using the marginal likelihood. Clear? Let's go ahead. So we want to compute the marginal likelihood. So the marginal likelihood is likelihood times prior, and we integrate out whatever is unknown, right? Likelihood we already know is Gaussian. It's already derived and defined initially. Prior is problematic because previously the prior was our function, so it was a Gaussian process. Now the prior is at those n locations. So that's why it becomes a Gaussian distribution with some covariance matrix which is derived from the covariance kernel that you have selected. The only problem is that it's a function of the unknown parameters theta k, which is still unknown. So this hyperparameters theta k and beta are to be computed. You are with me till now? If you are with me, then there is only one more step to be done, which is that I want to evaluate this integration. Right? If I have to evaluate this integration, I can see that it's a convolution of Gaussian. And convolution of Gaussian is Gaussian with certain parameter set. And what are the parameter set? If you write it in a generic way, these are the parameter sets that will be there. And we derive it using the property of expectation and variance that we have done in lecture 1 or 2. You basically write it in a linear form and then take the expectation and covariance, and that will give you the parameters. If you want to do some adventure, don't write it like this. Try to do the convolution directly, you will get this only. If you write in exponential form, do an addition of the exponential, then do an integration, do that adventure, and you will end up with this only. Okay? Y is not linear dependent on x. In this case, we have not assumed that. No, okay. If you go by a derivation, you assume y to be t, x to be y. Because we are doing it over t and y. There it is over y and x. So for one-on-one correspondence, here y is equal to t and x is equal to y. Then it will follow. And both, because we have to do that because both t and y are function of x. And that is not linear. We have not assumed anything there. Okay. Yeah. If x is normal distribution, probability of x is this CDF. What do you mean by that? No, when I'm writing PD, P it is not probability, it's a PDF. When I'm writing this P, okay, that's a very good point. When I'm writing this P, don't think of this as probability, think of it as PDF. Because in continuous, when I'm saying probability and all those things, I'm actually working with the PDFs. All the property of probability, the sum rule, product law also holds for PDF. So all of this P you see here is directly being acting on the PDFs. Because here also P I have written Gaussian, right? So that means these are the PDFs I'm talking about. So yeah, don't get confused with that. Yeah, that's a very good point, by the way. Sometimes I assume that you know that. Okay. So with that you arrive at this. So I have 5 minutes, so I don't think we'll go to prediction today, but we will do some simplification. So is everything fine till now? Is there any question? Yeah, go ahead.
How has taking a marginal likelihood?
Because y has been integrated out. So y was unknown. So I have integrated y. So y is now no longer in the picture. So now that is one point. The other point is that now theta has come into picture, theta k. Previously in the likelihood there was no theta k, but theta k is unknown. In the marginal likelihood, theta k has come into picture. So in one shot, by maximizing this, you are finding out the likelihood parameter beta and the prior parameter theta k. Okay, and also whatever is unknown has been integrated out. So that's how it helps. Total you cannot.
We cannot. If you marginalize y value, then doesn't we lost some information?
No. Marginalize, why will you marginalize? In fact, it is a better measure. Why you marginalization out does not mean you are losing something. It is just a statistics. Exactly. So you are not losing out anything. Anyhow, to start with, you have zero information about y. What information do you have about y? You have zero information about y. The only information you have about y is that it's a Gaussian process. That's an assumption we have made. That's a prior we have imposed. And even there the parameters are unknown. We have technically zero information about y. So what is there to lose? Yeah.
What are prior assumption on the mean affects our answer?
Yes, A will come into picture, exactly. But this is not prediction yet, but go ahead. No, this is going to be a loss function. I know what you are going to say. When we go to prediction, it will no longer be zero. But does it affect the answer? Obviously it does.
To take the mean of t.
No.
Because y mean.
Correct. There are two parts of this question. That's a very good question, first of all. First, as I said, if you have information, you should use it, correct? But if you do not have information and you bring neural network into picture, you are increasing the number of parameters. So you are increasing the computational cost. First point, right? Now, will that increase accuracy? In many cases, yes. But how much increase? Not significant in most cases. Why will not be in most cases not be significant? Think about it. If I make it a neural network or some linear regression model, the linear regression parameters will sit in this zero place. Now we will maximize, and you will maximize this to find out those parameters plus theta, correct? So if you don't have that, this theta gets tuned in such a way that it caters to those parameters, because ultimately nothing is known to you. So this theta will be different. If you bring those parameters into picture, you will get a different theta as opposed to when you don't have those parameters. So the idea is that you have now made your problem significantly more difficult without much gain in most cases. In some cases there will be gain. Okay. Just an anecdotal fact that my PhD 10 years from now, right, ago, was actually on developing an GP algorithm where we were modifying this mean and putting some mean as some function. Okay, so there is a class of problem where it does help, and that was my own PhD. We developed something known as HPCFE, which was combining PCFE and putting that PCFE as a mean inside a Gaussian process. Okay, but again, that increases the computational cost. Okay, any question from this? Otherwise, I'll just take 2 minutes and simplify it. Okay, the last expression here is the main expression. Okay, so how do you find out theta? theta star is equal to arg max theta probability of t given x. This is what we will do, which is a Gaussian, by the way, which is equal to arg mean theta minus log of Gaussian t given 0 Cn. Cn is Kn plus sigma y square I. Okay, this everyone agrees, nothing there. You can always take a log and negative sign makes max as mean. Why did I do that? Now open this Gaussian and tell me what will be there. How does a multivariate Gaussian look like? Two pi to the power minus n by 2. 1 by root 2 pi in case of 1. So 2 pi to the power minus n by 2. Determinant of Cn inverse 1 by 2. Exponential of minus half T transpose Cn inverse T. This is what you will get. And where is theta? Cn is a function of theta. I am not writing that. But do not forget, Cn is a function of theta. Cn theta, it is in terms of theta right now. And that you need to minimize or maximize. Take the log inside along with the negative sign. What do you get? Theta along with the negative side I am taking. So n by 2 log 2 pi, which is the most useless term. I am going to drop it. There is no theta there. So in that sense, it's useless, right? Plus 1 by 2 log determinant of Cn. Here is the important information. Log determinant, there are efficient algorithms for finding out log determinant. You should not try to first find determinant and then take a log. Check Python, check MATLAB. There are already inbuilt routines which can compute log determinant in a very efficient manner. You should use those. Okay, because otherwise sometime it creates problem. Okay, so there are efficient algorithms already there which allows you to efficiently compute and accurately compute the log determinants. The last term, half T transpose Cn inverse T. Okay, so this term you will drop. So what is your loss function then? Your loss function is half log determinant of Cn plus half is outside, so T transpose Cn inverse T. So this is your loss function. You do not need all these derivations. When you write a code, this is what you will need. And this will be in terms of theta. You will just maximize, in this case, minimize this loss function and get your theta. This is known as the negative log likelihood. Likelihood you know, negative you can see, log you can see. So this is known as NLL or negative log likelihood. So this is the negative log likelihood of the data. Very good question. You get a finite kind of number. It will not go very high or very low. So it's because the inside term is minimum, I mean, is negative sign. Why will I work with negative sign? And most optimization algorithms are for minimization also at the same time. So there is no reason as such. You can do that one also. You will realize that without log it can blow up and all those things can happen. With log that helps, and the negative signs helps because our mind is trained with minimizing a loss. So here that loss thing is kind of coming into picture, right? So what is the algorithm to conclude? This is only for training. Prediction is remaining. Remember that. Your input is data. Any other input? You have one more choice of covariance kernel. You have to specify what covariance kernel to use. Right? Step 1, you will find out L theta. Step 2, you will find out theta star. Done. You will return theta star. So all those derivations was to arrive at this L theta. Okay, so a 4-line, actually 2-line algorithm. I can combine 1 and 2 and that will become a 1-line algorithm. Okay. So this is how you train Gaussian process. Just the one thing is that you just need to, this is a non-convex optimization, keep that in mind. So it will able to use some gradient descent, not gradient descent, but yeah, some optimization algorithm which is iterative because it is non-convex. Okay, I'll stop here. Next time we'll go with the prediction. Thank you.